we're going to use what we know about the sign of the second derivative to help us determine where the graph of each function is concave upward and where it's concave downward. Remember, if the graph is concave upward, that means that the second derivative will be positive. And if the graph is concave downward, that means that the second derivative will be negative. So first things first, I got to find my second derivative. I can't find my second derivative without finding my first derivative. So here I'm starting with h of x equals x cubed. The first derivative, h prime of x, is 3x squared. Remember, for concavity, we want the second derivative, which means I got to take the derivative one more time. H double prime of x is equal to 6x here. And what I want to be thinking about right now is, where could my second derivative change signs from being positive to being negative? Because that's going to be where it changes from being concave upward to being concave downward. And if we're just thinking about, say, the sign change in h double prime, we thought about a very similar idea in the last section when we were talking about the first derivative. And we said when we were working with the first derivative, it can change sign when it was equal to 0 or where it does not exist. And that logic carries over here as well. H double prime will change sign at places where it's equal to 0 and places where h double prime does not exist. So I'm looking for really the same two scenarios here, except instead of working with the first derivative, I'm now working with the second derivative. So I'm going to start by taking 6x, my second derivative, setting it equal to 0 and solving for x. In this case, we can divide both sides by 6, and we end up with x equals 0. Now, this is not a critical number because critical numbers only apply to the first derivative, where the first derivative is 0 or undefined. For now, we'll call this a partition number of our second derivative. We'll come up with potentially a different name for it later on, but for right now, we'll just call that a partition number. Places where the second derivative does not exist, in this case, I'm going to look at the equation of h double prime, which in this case is just 6x. That's a polynomial, so h double prime is a polynomial, which means that we have no other x values here. We're not going to come up with any other partition numbers. So the only partition number that I've got here is x equals 0. And think about, okay, well, what did we do last time when we were trying to find the sign of the first derivative? And well, we made a number line. We made a number line for, say, f prime. But instead, this time, we want to be working with the second derivative. So I'm going to make a number line for h double prime of x. The one partition number that we came up with was x equals 0. And just for my own knowledge, we found that x equals 0 by saying, where is the second derivative equal to 0? So I'm going to put a little 0 right above that just so I know, hey, the second derivative was equal to 0 at that point. And now I can take a number on either side of 0 and plug that into, again, my second derivative, because that's what I want to know the sign of. So I'm just going to take a number on either side of 0 and plug that into h double prime of x. So I might start with, say, h double prime of -1, start on the left-hand side. Well, that would be 6 times -1 gives me -6. So that means that h double prime is negative on the left-hand side of 0, which means that the graph is concave downward on that side of our partition number. And then we're going to do the same thing on the right-hand side of 0. So I'm going to take, let's say, x equals 1 and plug that into our second derivative. So here, 6 times 1 gives me a positive 6. Remember, it's the sign that we're interested in, so that means h double prime is positive. That means my graph must be concave up on the right-hand side of 0. So when it comes to summarizing our answer here, we can say, okay, well, based on our sign chart right here, we know that our graph is concave up on 0 to positive infinity, and it's concave down on negative infinity to 0. That is where my graph is concave up, and that is where my graph is concave down. We're not going to include 0 in either one of those intervals because it's changing concavity there, and that'll actually have a fancy name that we'll talk about later on in this section. One thing I do want to point out before we move on to our next example is I would really highly encourage you to label your number lines with either the first derivative or the second derivative. It helps you keep your information straight, and it helps you remember what piece of information we're finding. Are we finding information about whether our function is increasing or decreasing, or in this case, are we finding information about the concavity of our function? So just be careful with those because later on in the section we will be working with both the first derivative and the second derivative. So we want to make sure that we have both of those straight, and we know when we're working with h prime and when we're working with h double prime. Let's look at one more example here. Again, I just want to determine where is this function concave up and where is it concave down. This time I'm working with f of x equals e to the negative x power. So I first of all need to find the second derivative. If I want to find the second derivative, I got to find the first derivative. So h prime of x. In this case, we're going to have to use our chain rule. So here we multiply by the derivative of our power, which would be -1 times e to the negative x, or negative e to the negative x power. There's my first derivative. For my second derivative, we'll just take the derivative one more time. Again, I'm going to need another chain rule for when I take the derivative of negative e to the negative x. So I'm going to multiply by the derivative of my power, which is -1, times negative e to the negative x power. And in this case, we actually end up with the exact same function we began with, e to the negative x power. So there's our second derivative. It actually ended up being the same as our first derivative. I'm going to, because I don't like working with negative exponents, I'm going to rewrite that as 1 over e to the x. Either one of these I think is fine if you're just finding the second derivative. But when it comes to finding our partition numbers, I always think that those positive exponents are easier for us to be working with. All right, so what's next? We have our second derivative. So now we want to think about places where f double prime is equal to 0 and places where f double prime does not exist. Well, if I take my second derivative, 1 over e to the x, set it equal to 0, my first step in solving this would be to multiply both sides by e to the x. And that is going to leave me with 1 equals 0, which is most definitely not true, which means we have no solutions to this equation. So no partition numbers there. I also want to go ahead and think about places where f double prime does not exist. For this particular problem, the thing that I am worried about is places where my denominator is equal to 0. So I'm going to take that denominator, e to the x, and set that equal to 0. Now, if you were solving this problem like we solved exponential equations back in at the very beginning of chapter 3, you might say, okay, well, your first step is going to be to take the natural log of both sides. Natural log of e to the x would just give me x, and then I would just need to look at, well, what is natural log of 0? But in this case, natural log of 0 is undefined. If you try to type that into your graphing calculator, it's going to say error domain, because 0 is actually not in the domain of the logarithm function. We can't take the natural logarithm of 0. It's not defined. What that means for me is that, again, I end up with no solutions. This is kind of, I think, an interesting case here, because what this means is I actually have no partition numbers. We ended up with no solutions when we set the second derivative equal to 0, and no solutions when we thought about places where the second derivative does not exist. So you might be kind of stumped then as to where do we go next if we don't have any partition numbers. We're actually going to go the same way that we've always been going. We would say, okay, well, let's go ahead and make our number line. So here's our number line. We're going to be working with the second derivative. Now, normally we would put a partition number right in the middle. We'd say, okay, here's our partition number. It's 0 or it's 2 or whatever it is. But in this case, I didn't have a partition number, which actually means I can pick literally any number that I want and plug that into my second derivative. What this means is that f double prime is actually never going to change sign. It's either always going to be positive or it's always going to be negative. So I can pick any number that I want and plug that into f double prime. I might say, how about 0? 1 over e to the 0, that would be 1 over 1, which is just 1. It's positive, which means that my second derivative is positive everywhere, which means it's concave up everywhere. Again, we could have picked any number that we wanted. If we had picked, say, f double prime of 1, this would be 1 over e to the first power, or 1 divided by e, which you could figure that out. Let me type that in real quick. You're going to get a nasty decimal, but 1 divided by e, that would give me, let's see, 0.37 if I round to 2 decimal places. But again, it's positive. That's what I'm interested in. The sign is positive. So if I want to wrap this problem up then and summarize the concavity here, this is, my second derivative is positive everywhere, which means that it's concave up everywhere. So that means that this graph is concave up on negative infinity to positive infinity everywhere. And then if I wanted to say, well, where is this graph concave down? It is concave down nowhere. So be on the lookout for problems like these. They are kind of interesting because if we don't have a partition number, it might kind of mess up your regular thought process. But just keep going. Don't overthink it. You're still going to go ahead and construct your number line for your second derivative, and you're still going to be plugging numbers in and checking the sign of that second derivative.